Sometimes on the periodic table we have certain elements that are in the third group on the periodic table, especially like phosphorus or sulfur. Those elements have the special ability to actually kind of hide away extra electrons. So in these two examples here, we have sulfur and arsenic. Both of the center atoms, or the central atoms, have more than 8 electrons total. I think they both have 10. So 8 would still be in the valence shell, but those extra 2 electrons would end up being stowed, or would go into the 3D periodic 3D block of the periodic table. So it's kind of interesting that they're able to do that. Things above the third period on the periodic table can't do that. So things in group period 1 or period 2 can't, but 3 and below can. And as you go down the periodic table as well, you can actually stow more than just 2. These are exceptions, and I wanted to show you what happens when you try the NAS method with these, or the needed, available, shared. So needed, available, shared. So in this first one, we have 5 elements that would fulfill the octet rule. So 5 times 8 would end up being 40 electrons. We have 34. It actually counted for us. When we subtract these, we end up with 6 shared electrons, which when we divide by 2 would give us 3 bonds. Now, right away, this shouldn't make sense. 3 bonds, but we have 4 different things that we would need to bond to. So because of this, this is the result. Sometimes you have more electrons on your central atom. When it's in the third period or below, that's acceptable. So this is still the correct structure of it, is just an exception. Something similar happens here with the arsenic one. We have 6 different atoms following the octet rule, which would be 48 for my needed. I have 40 available, so I would have 8 shared, resulting in 4 bonds. But I actually need to have 5 bonds. So when you have these things happen and it doesn't make sense, like you have something that you just leave off, you have a problem. So sometimes this method for exceptions doesn't always work out when you have kind of these odd symmetries. So what I'd like to do next is I'd like to go through some examples of some Lewis structures that we'll talk about. The first one is actually an organic compound, which has 2 carbons, which would be referred to as F. Now, this is kind of has 2 parts to it. Because we have those 2 carbons, and because of what we know, this one actually doesn't really have one central atom. It's going to have both carbons in the middle, but we're still able to do the NAS method. So we would have 8 electrons on each carbon, 2 electrons on each hydrogen. So we would have 8 times 2, which is 16, plus 8, which ends up being 24. We have available to us, we have 4 from each carbon, plus 1 from each hydrogen, which would give us 12. So 8 from the carbon, 4 from the hydrogen would result in 12. When we subtract that, we have 12 shared, meaning 6 bonds, because we divided it by 2. So we have the 2 carbons. I already kind of said those are my central. Sometimes, especially with organic chemistry, you can have more than one central atom. We have the 2 carbons. With everything that's left, I just kind of draw it symmetrically around what I have. So I would probably put H's kind of all around. So we start off, we can have a total of 6 bonds. So 1, 2, 3, 4, 5. I start off by giving everything 1 bond and seeing how many that is. So in this case, I used 5 of the 6. So I have to make a decision about where to put the 6th. Now, if you remember, hydrogen has the duet rule, not the octet rule. All of the hydrogens at this point have a full outer shell. The carbons, however, do not. So we'd end up having another bond on the carbons, resulting in a double bond. So we have a total of 12 shared electrons now, which is how many we have available to us, resulting in a complete Lewis structure. Next, we're going to take a look at HCN. So we have N, A, and S. So hydrogen, again, follows the duet rule, which would need 2 electrons. The carbon and the nitrogen would both have 8, so that would give us a total of 18 needed electrons. We have available to us 1 from the hydrogen, 4 from the carbon, and 5 from the nitrogen, which would give us a total of 10. This would result in 8 shared electrons. When we divide that by 2, it would be 4 bonds. We need to make a decision about central atom. We have a carbon. If you have a carbon, it's going to be the central atom 99% of the time. So carbon, and then I'm just going to put an H on one side and an N on the other. Sometimes in these two, usually if it's written like this, if you have 3 different things, it kind of gives you a little bit of a clue when they write the formula. You generally want to keep it in the same order, just as kind of a hint. So we have a total of 4 bonds. We're going to start by putting 1 bond on each item. Right now, hydrogen now has a full outer shell, but my carbon has 4 and my nitrogen has 2. So I used 2 of the 4 bonds. I have 2 left. I can't put them here because hydrogen already has a full outer shell, so I'm going to have to put them both between the carbon and the nitrogen, resulting in a triple bond. So if I count up the bonds, I have 1, 2, 3, 4, which would be my 8 shared electrons. I have 2 electrons left that are available, so those are going to go on my nitrogen, because without them, nitrogen doesn't have a full octet. So that would be my Lewis structure. Instead of PF5, we're actually going to take a look at an ion. We're going to do ammonium, which is NH4, and it has a +1 charge. I wanted to point out what happens with these ion ones because it's a little bit different from what we're used. There's one more thing that we'll do with them. So we have 4 hydrogens and 1 nitrogen. So for my needed, I have the nitrogen, which would be 8, plus 8 from my 4 hydrogens, resulting in 16. I have available to me right now 5 from the nitrogen and 4 from all of the hydrogen, resulting in 9. Here's the thing, though. With the available, we have to take into account the charge. When we have a +1 charge on any ion, that's indicating that we lost an electron. So instead of 9, we're going to say 8. So we'll have a total of 8 shared electrons, meaning 4 bonds. You may have noticed the brackets here. What those brackets are indicating is that you have a charge. So you're actually going to put your whole Lewis structure in a bracket. So I'm going to put a big bracket on here. Nitrogen will be my central atom. I only have 1 nitrogen. And then I'm going to put my 4 hydrogens kind of around it. I usually do it kind of at a diagonal here like I did here. If you put it 1 on each side, that's fine too. Right now we're not real particular about the location, especially in a Lewis structure. So we need 4 bonds. We have 4 things we need to bond. It works out perfectly. So we're going to have 1 bond between each hydrogen and the nitrogen. I have 8 shared electrons. I only have 8 available, so I don't need to have any lone pairs there. The last thing, though, you want to make sure you're still including your charge. So in this case, we have a +1. So you So just to reiterate, when you have a charge, you need the brackets around your whole Lewis structure, and you do also need to indicate your charge. Because if you don't, it's not showing that it's an ion. Our last example here, we have iodine. Oops, we want needed here, not iodine. Needed, available, shared. So for needed, we have 3 atoms that would have a full octet, which would result 3 times 8 is... each iodine has 7 valence electrons, so 7 times 3 is 21. And this one is, instead of having a positive 1, we now have a negative 1, so we're going to add an electron. So we'll have 22 electrons, resulting in 2 shared electrons. Now, remember what happened before? We have 1 bond, but we have 3 things. So that's kind of a clue that you have an exception. Obviously, iodine is going to be the central atom because we don't really have another choice. If we just have the 1 bond, something's wrong. So this is also an exception. We also need our brackets. So we're going to put in that second bond. Keeping in mind, we need a total of 22 electrons. Now, we used up, right now, we have 4 of our 22 electrons. We have 18 left. It makes sense to have lone pairs of electrons so that each of the end iodines have a full octet. So now both of the ends have a full octet. So we just used up 12. So 18 minus 12 means we have 6 left. So you would think iodine, you would just have kind of 2 pairs, but you're actually going to have 3 pairs here. So when this happens, you kind of draw them catty corner. Again, this is an exception. It's kind of an odd one. We have an extra pair of electrons on the central iodine. It's just what sometimes happens. Iodine is a very large atom, so there's kind of more space to include those extra electrons. So this is just kind of a review of everything that we've talked about with this. Most things follow the octet rule. Carbon, nitrogen, oxygen, and fluorine always follow it. Boron and beryllium can sometimes have less than 8. Second row elements can't exceed the octet rule. It has to be period 3 or beyond. The third row and heavier elements often satisfy the octet rule but can exceed by using some of their d block orbitals. When we write a Lewis structure for a molecule, we want to make sure that that our electrons match. We don't lose any electrons. We don't add extra electrons. So up to this point, we've only talked about covalent Lewis structures. They're the ones that are more important because we're going to actually take a look at the geometry with them. However, it is good to know how do you draw an ionic dot diagram or an ionic Lewis structure. You want to think back to what's happening. Covalent substances share electrons. Ionic substances transfer electrons. Because we're transferring an ionic Lewis structure is going to look very different. So let's take a look at sodium chloride. This is an easy example. So sodium by itself has 1 valence electron. Chlorine, I'll make green or red, has 7. Okay. What's going to happen is sodium is going to donate its 1 electron to the chlorine, which makes the ions. So we're going to have sodium in brackets with a +1 charge. Now it's customary not to draw any dots in around sodium because the 1 valence electron it had, it no longer has. It does have a full octet below, but you usually don't draw it. And then chlorine now has a full octet. And again, notice how I'm drawing them paired. So we have sodium and chlorine's ions, so that would be my Lewis structure. So ionic things act differently than covalent, so we draw their Lewis structures differently. So this would right here would be what I would expect for you to draw for an ionic substance. So just like with the naming, with the Lewis structures, there's usually just kind of an ionic one thrown in. You won't have, it won't be real obvious that you have it. So the next one, strontium bromide, it's a similar situation, but strontium has 2 valence electrons, and bromine has 7. Okay. So similar situation. One of strontium's electrons is donated to bromine. However, what happens here is that strontium still has a leftover electron. Okay. When we are ionic bonding, we can't have extra electrons. So this is kind of the reason why we swap and drop. We have to make sure that we don't have random extra electrons like that. So we actually need a second bromine here to take that electron. So this electron will go to the other bromine. So now strontium has a +2 charge. And then we're going to draw 2 bromines. With a -1 charge. Both have full octets for both bromines. My dot kind of blended in with my R there, so I'm going to fix that. You want to make sure your dots are clear with this and paired just like always. So that would be my Lewis structure for strontium. You don't see these a lot, but it's still good to know.